Welcome everyone to another mini course at Physics Latam. Today we are honored and very happy to have Professor Chiu-Chu Liu giving a mini course on topological string A model. Melissa Liu is a professor of mathematics at Columbia University. Her research interests include algebraic geometry and symplectic geometry. She earned her PhD in 2002 from Harvard University under the supervision of Yao. She won the Morningside Silver Medal in 2007 and was an invited speaker at the International Congress of Mathematics in 2010. She has made important contributions to the foundations of open Gromov-Witten theory with Jun Lee and Kevin Liu and Jian Shou. She developed a mathematical theory of topological vertex. With Qin Yao, she proposed a new definition of quasi-local maps in general relativity and proved its positivity. With Florent Schaffhauser, she extended Atiyah and Bott's work on the Yang-Mills equation over Riemannian surfaces to plane surfaces. And with Bohan, Fan, and Yu Shun, she proved the remodeling conjecture for all symplectic toric Calabi-Yau threefolds or bifolds. We are very happy to have her this and next week to teach us about her research on Gromov-Witten theory, topological string A model, the topological vertex, and the remodeling conjecture, and also current results. Remember to raise your hand at any point if you have any question, and I will leave you with Melissa. Please go ahead.
Okay, thank you so much for the invitation and a very nice introduction. It is my great pleasure and honor to give this mini course here. So this mini course will consist of 4 lectures. This is the first lecture. So the title of my mini course is A Model Topological String Theory. So let me give you a brief overview. Gromov-Witten invariants, roughly speaking, are virtual counts of parameterized complex algebraic curves in a complex projective manifold, so which is a compact submanifold of a big complex projective space. Or more generally, they count holomorphic curves in a compact Taylor manifold X omega J, where omega is a symplectic structure, which is a closed non-degenerate two form, and J is the complex structure. They are compatible together. They define a Taylor structure. Or even more generally, there's a symplectic approach to Gromov-Witten invariants, where we allow almost scalar manifold in the sense that here J can be just an almost complex structure, which is not necessarily integrable. And then in that setting, we count J holomorphic curves or pseudo holomorphic curves. So this course, we will mostly talk about the algebraic approach. Yeah, it is relevant to A model topological strings. I'm a mathematician. So Gromov-Witten theory can be viewed as a mathematical theory of A model topological strings. So this is my understanding of A model topological strings are Gromov-Witten invariants. Algebraic, so as I said, there are 2 approaches to define Gromov-Witten invariants. Algebraic Gromov-Witten invariants have been defined for general complex projective manifolds in all genera. So here the genus is the genus of the domain curve. Since it's a parameterized curve, it actually counts maps from curves to your target. And symplectic Gromov-Witten invariants are defined for general compact symplectic manifolds in all genera. So the foundations of algebraic and symplectic Gromov theory was established in the 90s. Open Gromov-Witten invariants on the other hand, are virtual counts of parameterized holomorphic curves in a compact Taylor manifold, or more generally, parameterized pseudo-holomorphic curves in a compact almost Taylor manifold with Lagrangian boundary conditions. So they count maps from border Riemann surfaces with holomorphic maps from border Riemann surfaces to your target Taylor manifold, such that the boundaries are mapped to a Lagrangian submanifold in the Taylor manifold. Recall that in general, so the Taylor manifold is complex manifold. A Lagrangian submanifold is a submanifold, real submanifold whose real dimension is equal to the complex dimension. So it's half-dimensional submanifold, such that the restriction of the symplectic form to the submanifold is 0. Yeah, so open Gromov-Witten theory can be viewed as a mathematical theory of A-model topological open strings. Open Gromov-Witten theory is still pretty open in the sense that they are not defined for most general compact symplectic manifolds, and they are not defined for general Lagrangian submanifold. But in this course, later we will talk about so-called toric Calabi-Yau threefolds. And for such toric Calabi-Yau threefolds, open Gromov-Witten invariants have been defined and computed. So here is the outline of this mini course. So the first part, I will give a brief review of Gromov-Witten theory for general target from the algebraic approach. And the second part, I will talk about the topological vertex. And the third part is about the remodeling conjecture. So now let me give you a rough idea of what the second and third parts are about. So the large N duality proposed by Gopakuma-Vafa relates A-model topological string theory or Gromov-Witten theory on Calabi-Yau threefolds and Chen-Simon theory on three manifolds. So these are gauge theory on real three manifolds. And based on this large N duality, which is one of the many string dualities, Agnagich, Clem, Marino, and Vafa proposed the topological vertex, which is an algorithm on computing all genus open and closed Gromov-Witten invariants of smooth toric Calabi-Yau threefolds. So that's the so what we will do is we will discuss a mathematical theory of the topological vertex, and there will be also some updates are the recent developments and refinements of this topological vertex. So that's the second part of this course. So the third part of the course is the remodeling conjecture. The remodeling conjecture was proposed by Bouchard, Clem, Marino, Pasquetti, and it relates it's another algorithm to compute all genus open and closed Gromov-Witten invariants. And this algorithm works for symplectic toric Calabi-Yau three manifolds and also three orbifolds. And they relate this open and closed Gromov-Witten invariants, or more generally, orbifold Gromov-Witten invariants, to invariants defined by applying the Chekhov-Aina-Arnton topological recursion to the mirror curve of this toric Calabi-Yau threefold. It can be viewed as version of all genus open closed mirror symmetry. Yeah, so this is an overview of this mini course. So now let me start with part 1, which is an introduction to Gromov-Witten theory. So as we said, Gromov-Witten invariants are virtual counts of, so since we are in the algebraic setting, so we consider a non-singular projective varieties over the complex fields. So it's a compact submanifold, big complex projective space. And so we will introduce notion of stable maps, and Gromov-Witten invariants are virtual counts of stable map. So to define stable map, let's fix two non-negative integers g and n, and some effective curve class. So some second cohomology class in X with integral coefficient, which can be represented, which can be written as like a non-negative combination of algebraic curves, the classes of algebraic curves. So a genus G m-pointed degree beta pre-stable map to X. So we first define pre-stable map, and then we will impose stability condition. It is a morphism. So from a curve, so a curve to X. So here the domain, like C, is a reduced connected projective curve with at most nodal singularities, such that its arithmetic genus is G. So if you smoothing the node, you get some smooth Riemann, you get some smooth Riemann surface or complex algebraic curves, and this G is the genus of that smoothing. And here, so the domain is such a curve, and here x1 to xn are distinct and older points on C, which are smooth. They are away from the nodes. So 1 and 2, so the data 1 and 2, just the curve together with this MR point. This is called a genus GM pointed pre-stable curve. So it's a genus G nodal curve, and then you also have M points which are older and smooth. So finally, the third part is about the map. So we require that, so the map, so if you push forward the fundamental class, and when it's actually, so if it has several irreducible components, you take the sum over the push forward of the fundamental class, it's equal to this beta called the degree of the map. So G is the genus of the domain, N is the number of marked points, and beta is the class of the degree of the map. So this defines a pre-stable map. And then, so we are going to define some moduli space. So we want to say, like, when are two such things considered as like equivalent or isomorphic. So suppose that you have two pre-stable maps of some genus M pointed and degree beta in the above sense, Cx1 to xn and the map U to X, and C prime x1 prime and xn prime and together O. So an isomorphism of two pre-stable maps is an isomorphism of the domain as a pointed curve. So phi is an isomorphism from C to C prime, mapping xi to xi prime, such that this diagram commute. So this is called an isomorphism between two pre-stable maps. And in particular, this defines the automorphism group. Yeah, it's an isomorphism from a pre-stable map to itself. So now, wait, oh yes. So we say a pre-stable map is stable if its automorphism group is finite. Okay, so that finished the definition. So yeah, so that M bar G and X beta denote the moduli of G and G M pointed degree beta stable maps to X. So this moduli space is a proper Dillman-Mumford stack. So if you are if you like the like differential geometry or topology more, so this moduli space you can think is a compact Hausdorff, but usually singular orbifold. So under assumption, you can think locally, it looks like some possibly singular scheme quotient by a finite group. So now at least we now understand its set theoretically, and yeah, we also quote this fact that we have this kind of structure. So now let's introduce some maps. Oh, so there are like evaluation map at the ice mark point. So for each mark point, so given a stable map, and you can there's an evaluation map to at the ice mark point, sending this stable map to like uxi in X. So there are n of them, one for each mark point. So here we have, so there's a map, so M bar GM plus 1 X beta, forget to M bar GN X beta, given by forgetting the last mark point. So this is mostly okay, but in some cases, when you forget the last mark point, it will become unstable, and then you need to contract some component to make it stable. So this is the morphism from M bar GM plus 1 X beta to M bar GM. And so there's a map to evaluation to the last mark point. But actually this forgetting map can be viewed as it can be identified with the universal curve, and the evaluation map at the M plus 1 smart point can be identified with the universal map. So more precisely, so if you take a point in this moduli space, M bar G and X beta, so it is represented by some stable map, then the fiber of this is just the domain. And also there are n sections correspond to the M mark points. And finally, if you restrict this evaluation map to the fiber, is the map. So in this sense, this can be, M bar GM plus 1 X beta can be identified with the universal curve, and the evaluation at the last mark point can be identified with the universal map. So let's see. So we also have, so here, so we have, So I'm showing this on the computer, so which is not my iPad. So, but I think it should be okay. So now like we have this m bar gm plus 1 x beta, and then so say like curly x is this m bar gn x beta, and this can be identified with the universal curve over the moduli space of stable maps. So here we have a forgetful map. So, okay, so this is forget the last mark point and possibly contracting some unstable thing. And this is, we just forget the map, but we don't stabilize the domain. So yeah, you just forget the map. So so the domain, the target is moduli space of genus GM pointed pre-stable curves. And then over this moduli space, there's a universal curve, which can also be, yeah, there is a universal curve. And then yeah, and then this diagram, yeah, so this universal curve is the pullback of this universal curve. So then we have so this moduli space. So because like because it's just pre-stable, so I mean this moduli space, so there are like the point here can have like infinite automorphism groups. But it's a smooth, but it's still smooth in the sense that it's a smooth arting stack and of dimensions 3g minus 3 plus n. And it can be written as a disjoint union of infinitely many strata. So the stratum, so the strata are like labeled by the topological type of the domain. Yeah, so we would like to label them by dual graphs, which I will say a few more words about the dual graphs later. And then you see that if we impose the stability condition, like required like the automorphism group of the curve itself as a pointed curve is finite. So this is an open substack, and this is a proper and smooth Deligne-Mumford stack. So it's just a compact complex orbifold of this complex dimension. And this is a union of, yeah, so this is a disjoint union of finally many strata. Yeah, so this is the set of like stable dual graphs and the stable set of dual graphs. So this is a subset. Oh, and yeah, so m bar gn is non-empty if and only if 2g minus 2 plus n is greater than 0. So in particular, so you see that when genus is 0 and you have 1 or 2 mark points, then it cannot be stable. And also when genus is 1 and you have no mark point, also you have like infinite automorphism group. And these are the unstable cases. The other cases are stable. So for the other cases, this moduli space is non-empty. Right. So then now this M bar G and the moduli space of stable maps is also disjoint. So this is proper. So it's disjoint union of finitely many strata and labeled by decorated dual graphs. So let me yeah, so describe, oh, what happened? So let me first describe the dual graph for like the moduli of pre-stable curves. So suppose that you have a pre-stable curve, which is just a nodal curve. So you can normalize it. So C tilde is you just like resolve the node. So then C tilde becomes smooth, but it's possibly disconnected. So for each kinetic component of C tilde, or equivalently each irreducible component of C, you associate a vertex of this graph. So the vertices are in one-to-one correspondence to the kinetic component of C tilde, or irreducible component of C. So for each node, you associate an edge, and for each so the flag is how does they fit together. So if you yeah, so if a node is so if two yeah, so if two irreducible component intersect at a node, then in the dual graph they correspond to two vertices connected by an edge. So a flag EV is an edge, a pair where E is an edge, V is a vertex, such that the vertex is one end of the edge, right? And then so this is a flag in the dual graph if and only if the corresponding the node associated to the edge is in the irreducible component associated to the vertex V. So that's the dual graph. And then also, so we also have a label. So each vertex is assigned the genus of CV. And finally, for each mark points, we have an leg. So each mark point is on some CV, and we attach the leg to the vertex V associated to CV. So the arithmetic genus of the whole curve is equal to the first Betti number of the graph plus the sum of the genus of GV. So is there a chat? So why do you say tilde C is possibly disconnected? Okay, so let's see. Yeah, so yeah, I was going to, oh. So yeah, so yeah, maybe okay, so this is not, so if, yeah, I wish I can draw it, but so now so I'm just saying that, for example, if you have a genus 2 curve degenerated to like degenerate to a curve with one node where each irreducible component is a genus 1 curve. So after you normalize it, it becomes a like disconnected union of two genus 1 curves. Is this? Oh, great. Right. So Yeah, so that's so I described, so yeah, actually, as you can see that the so for each yeah, so for each pre-stable curve you can associate dual graph. So curves with the same like dual graph have the same underlying topological space. And yeah, so for each gamma, so this form a stratum of, oh, do I have more? Oh. Okay. Yeah, so this form a stratum of the moduli space of pre-stable maps. So then now let's describe the like stratum of strata of the moduli of stable maps. So suppose that now you have this stable map. So yeah, actually first you have this decorated graph associated to the domain, which is a pre-stable curve. And then you just one extra like data, which is for each vertex, you also decorate by the degree, which is a second homology class in your target X. And moreover, because of stability condition, if beta V is 0, that's equivalent to say that CV is contracted to a point under the map U. And then in order for the map to be stable, then so then this curve, so this component needs to be stable, which is equivalent to say 2GV minus 2 plus MV is greater than 0. So here MV is so the number of special points on CV. So the special points are the pre-image of mark points and the pre-image of nodes. Yeah, so the automorphism cannot move those points. Yeah, and of course, like the total degree of U is the sum of the degree of each CV. Okay, so that's a brief description of, so now like the decorated graph of like stable maps is like decorative graph of the pre-stable curve together with this extra label for the degree. And so, and also we can write, yeah, so M bar G and X beta is a disjoint union of strata. Yeah, labeled by this graphs. Okay. Yeah, and as you can see, like up to automorphism, this lower yeah, this each stratum is up to some finite group action is a product of like smaller moduli spaces. Okay, so yeah, so let me give you an example. So yeah, so as we said, this M bar 0, 2 is actually empty, right? So you have genus 0 curve with two mark points. So it can never be stable. Oh. Why is the second homology class considered are not other kind of homology? Okay, so let's consider the case where your domain is just a smooth genus G curve, right? So you want to consider, yeah, so you want to consider like the on the fundamental class of your domain is is in like a second homology. So the image is in the second homology of the target. Does this answer the question? Oh, the question is, why is the second homology class considered and not other kind of homology? Okay, I don't know if this. Yes, for example, why not H1 or H3? So first, because yeah, so the domain, yeah, we want to, so why do we want this? So yeah, so maybe let me say the following. So we can first just consider moduli space of all stable maps. But then, I mean, there are just infinitely many connected components. So then we want to somehow separate, yeah, and then we want to have, so when we define invariance, we want to be able to define the like genus G degree. We want to define an invariant for some fixed topological type of a domain, which, yeah, is given by the genus, and also fixed topological type of the map is given by the degree. So now, yeah, so the why not H1 or H3? Because if you consider this map from curve to your target X, so first the curve is like yeah, two manifold, so there's no H3. And for H1, actually, we will use H1 when we later discuss open Gromov-Witten invariants. So because for open Gromov-Witten invariants, you count maps where the domain is like border Riemann surface. So actually, in that case, we are going to also consider H1. So the so-called winding numbers, which are, so you consider the boundary circles, and they represent, and you consider the boundary circles. So they map to the target. So they represent classes in like the first homology. So when we do open, we will consider actually relative H2 and also H1. Does this answer? Oh, okay, yeah. Oh, great. Okay. Yeah, thank you for the question. So now let's consider yeah. So M bar 0, 2 is like yeah, the moduli of like stable genus 0 two-pointed curves, and this is empty. There's no such curve. But then the but the pre-stable curve, yeah, so actually it has dimension -1. Why? Because if you look at, so now we consider, I will give you, so this has infinitely many strata. So I'll just give you some examples of strata in this moduli space of pre-stable curve of genus 0 with 2 mark points. So the top stratum is the top in the sense that it's like so actually if you compute the dimension, right, as a stack is 3G minus 3 plus n, in this case is actually -1. Could you share your notes? Let's see. So,
Yes, don't worry. We will post the lecture notes at the end of the lecture on the website.
oh, okay. Yes. So Yes. So yeah, actually, so if we look at the yeah, for the stratum in pre-stable curves, so because all the so the moduli space is still smooth. It can have like negative dimension because you see, for example, top stratum is just it's just like if you don't consider the automorphism, it's just the like 1 point, right? It's just a P1 with two mark point, and there's no moduli, but there's automorphism group C star. So this top stratum is just a point quotient by the action of C star. So that's why we view this as like dimension -1 as a arting step, which point has dimension 0, and you quotient by a group of dimension 1 is -1. So this moduli space is somehow smooth of dimension -1. Yeah, so and then in this case, so yeah, so you see this vertex, it has like one vertex, no edges. And in general, recall that number of edges is equal to the number of nodes. And if you have a node, then your strat will decrease, each node will decrease the dimension of the strata by 1. So now let me give you another example. So you can have a chain. Yeah, so you see, you can have a dual graph where you have m vertices and you have two legs in the end corresponding to the 2 mark points. And then, so this vertices are connected by edges. So there are m vertices, m-1 edges, and 2 mark points. So I draw the corresponding like picture for, yeah. So this is curve. So this is still yeah, this still has no moduli. So it's a chain of P1. And then you see each P1. So we have m vertices. So you have like m P1s. And each P1 has automorphism like C star, like rotating it, fixing this 2 special point. So it has automorphism of like, yeah, C star M. And then this, I see. So this yeah, so this, yeah, so you see this, there's a strata, yeah, associated to this dual graph. So this strata is like a point mod C star M. So this strata is like dimension -m. Yeah, so you see that it's dimension m-1 less than dimension -1, which is consistent with the fact that it has m-1 edges. Yeah, I guess usually like people do examples for like the stable thing. So I just want to give you an example of like unstable thing. Yeah, I hope this makes sense. Okay, let me okay, so here's a very simple example of moduli space of stable maps. Yeah, so let's consider like yeah, so let's consider the target as P1, right? So like we consider map from like genus G curve, M pointed genus G. Genus G M point is degree D stable maps to P1. So the second homology P1 is generated by the fundamental class. So I mean, so this is one dimensional. We denote it by P1 comma D instead of P1 comma DL. Okay, so what is the most, let's consider the most simple case we might consider, and it's not empty. So genus 0, no mark point, and degree is 1. Yeah, we cannot do degree 0. If we do degree 0, it's empty. So, but then what is degree 1 map? Yeah, so then you see that there's only 1 point, and it's just the identity map from P1 to P1. And this map has no automorphism because you cannot find, because it's identity map, if you have non-trivial automorphism, it won't make the diagram commute. So the only automorphism is also the identity. And then now, yes. Okay, so this is a point. So now recall that, let's see, in this example, we have so recall that the universal curve is moduli space of genus 0, 1 pointed degree 1 map to P1, right? And then there's 1 point, so we can evaluate. But what's going on here? So it's evaluation to P1. And basically, you see, this is just G. So this can be viewed as the universal. So basically what happens is this space is just a point, and the universal curve is just P1. And this evaluation 1 is just identity. Yeah, and the section, okay, so sorry, it's just the identity, and this is the universal map, which is the identity map. Okay, this is the right. So in this case, okay, so this is a point, M bar 0 on P1 1 is just P1. So how about, so 2 points. So now we know that M bar 0 1 P1, we already know that it is a P1, and evaluation, so you can think this evaluation, so basically you can think P1, and it's the map is just identity map, but then you can the point is any point on P1, and the moduli is just that where that point is, and then evaluation map is is identity map. So this is an isomorphism, right? So now let's consider M bar 0 to P1 1. So you see that what is the universal curve? So this is a P1, but you see so the universal curve is just P1 cross P1, right? Because for any point in the moduli space, it's, the domain is P1. So it's just P1 cross P1. And now, because we have 1 point, so their section correspond to the mark point. So this section is just tell you which point so the base tell you where the point is, and the section send it to the mark point. So this sigma 1, so if we identify this with P1 and this with P1, so this is P1 cross P1. And also the evaluation map. So you have P1, P1. So we see that the evaluation map is just map to map each fiber identically to P1. So in this simple example, so the M bar 0 to P1 1 is P1 cross P1. The forgetting the last mark, the second mark point gives you the first projection, and then the evaluation map to the second. Actually it's, the isomorphism to P1 cross P1 is given by evaluation 1 cross evaluation 2. So this is a very simple example of moduli space of stable maps. Yeah, and also universal. Yeah, so if you go, yeah, if you go one more, then it will become more interesting. Let's see. One. Is there a relation between the number of mark points and stability of maps? Yeah, so what I can, the number of mark point and the stability of maps. Yeah, all I can say is you can, okay, let's do it in the following way. So the idea is that if you have some stable map whose domain is already a stable curve, yeah, because it's, so to be an automorphism of a stable map, it first has to be automorphism of the domain as a pre-stable curve. So if the domain is already a stable curve, then yeah, then it will be a stable map. So now so more generally, so what, when is the domain a stable curve? So it is like when you consider each irreducible component, or CV in the normalization together, each CV together with the special points, which are pre-images of nodes and mark points. So each CV, V correspond to an irreducible component, each CV. So if it's already stable curve, then it's fine. If it's not stable, then it cannot be contracted to a point. So I don't know if this answers the question. Okay, great. Oh, actually, so it's 9:56, but since I'm starting a new section, maybe it's a natural place to take a break. Okay, so let's move to the next section. So as we said, M bar G and X beta is usually singular. So in general, it does not have a tangent bundle, but it has a virtual tangent bundle. Under our assumption, actually there's a two-term complex of vector bundles. So we should view them as the virtual tangent bundle. So there's a map phi from E0. So E0 and E1 are vector bundles on the moduli space. So they have certain rank. And there's a map between them. So at any point, this is a linear map between vector spaces, but the rank of this map can jump. The kernel is known as the tangent space at the point, and the co-kernel is the obstruction space. So the dimension of kernel and co-kernel can jump, but but the dimension of kernel minus the dimension of kernel is, yeah, always equal to the rank of E0 minus rank of E1. So this rank is the rank of the virtual tangent bundle is a constant when we fix genus number of mark points n and beta. So that's called the virtual dimension. And let's look at this more carefully. So we are going to describe this tangent space and obstruction space. space at each point. So let's consider a point in this moduli space represented by a stable map with domain Cx. Lower underlying x is like shorthand notation for x1 to xn, and U is a map from C to the target x. So at this point, we have the following short exact sequence of complex vector spaces. So as I said, I want to describe the tangent space T upper one lowercase c at this point, and the obstruction space T upper two lowercase c at this point, cos c. So they actually fit in this short exact sequence of complex vector spaces. So here extension so omega c x1 to xn OC. So this is so here this vector space is the space of infinitesimal automorphism of the domain curve. So yeah, so this is like the Lie algebra of this. So if this is finite, then this is 0. And also when C is smooth, right? So then C is smooth, that omega C is like, so when C is smooth, so this is just the space of holomorphic vector fields on C, which vanishes at this mark point. Yeah, so if you have some infinite one parameter family of automorphism, and then you see that's generated by such a vector field. So that's this part. And for the extension one is the infinitesimal deformation of this mark curve. So and then so here and this part, so this is the infinitesimal, so H0 C, the pullback of tangent bundle under the map U is the infinitesimal deformation of this map U when you fix the domain C. And H1 is the obstruction to deforming the map, infinitesimal, so it's the set of like infinitesimal obstructions of deforming the map U when you fix C, right? So you see this part is about automorphism or domain deformation of the domain. So this like gives you the moduli of the domain. But if you, and this gives you the deformation of the map and obstruction to deforming the map. So yeah, so that's that describe the tangent and the obstruction space at the point. So now let's see. So let's consider. So we have this moduli space of stable maps, and we forget the map, and so this is the just forget the map and remember the domain, and then this is a smooth arcing stack of dimension. The dimension is like dimension of deformation and minus dimension of the automorphism. So this is always 3G minus 3 plus n. So the deformation, so these two spaces can have different dimensions at different points. But this dimension is constant over this whole moduli space for fixed Gn. And so then this so there's a relative, so this is smooth, but this is so this map is like virtually smooth of relative dimension because there's no obstruction to deforming the domain. So the obstruction comes from deforming the map. So H0 and H1 are the like deformations and obstruction to deforming the map. So this relative dimension is like you fix a point in a base and look at the fiber. That's the virtual or expected dimension of the fiber. So so then this is the relative virtual dimension, and this is just can be computed by Riemann-Roch. So we know like the pullback of the tangent bundle is it's a complex vector bundle over the curve C. What does virtually smooth? Yeah, so virtually smooth just means it's, this is a terminology. This is older terminology. It means like it's not actually smooth, but it's virtually smooth. Oh, maybe Daniel, do you have some comments about this? Yeah, so this map is virtually smooth, and the relative virtual dimension is given by this, and then this is this can be computed by Riemann-Roch, right? So this is a vector bundle over the curve, so it should be the degree of the bundle plus rank to bound times 1 minus g, and then. But the degree of the vector, the pullback is the same as like, so this degree is the same as like you pair so this integral sign stands for the pairing between beta, which is second homology class, with the first chain class of tangent bundle, which is the second cohomology class. So this is an integer. And now this rank of the tangent bundle is just the dimension. So you see that this is the relative virtual dimension. It's just given by this. And so it's constant when we fix beta and g. And then the virtual dimension of the whole moduli space is like the dimension of this like moduli of domain plus this relative virtual dimension. So this is the formula for, so the virtual dimension. So this is the rank of the virtual tangent bundle. Okay, so this is like, then fortunately, like, I should say, I'll probably add it later. So in algebraic geometry, this virtual fundamental class was constructed by Baron based on the intrinsic normal cone by Baron Fantacchi and also by Li and Tian. So there's a virtual fundamental class, which is a class in the expected degree, right? In the very nice case, when this is actually a smooth orbit compact, when this is actually smooth, then there's a fundamental class, and this will be the fundamental class. In that case, this virtual dimension will be the actual dimension of your moduli space. So here are the nice case. So if you have a non-singular projective variety, so a projective manifold, we say it is convex if, so this is a condition on genus 0 stable maps, because you just cannot expect it for higher genus. So we say this, it is convex if for any genus 0 stable map, you don't have H1. So then this means, so this condition will guarantee that the map given by forgetting the map, remembering the domain, is not only virtually smooth, it's actually smooth. So in this case, the moduli space of genus 0 stable maps will actually be smooth. And examples of like convex targets are projective space, or more generally Grassmannians, which include projective spaces as special cases, or more general, like generalized flag varieties, like this kind of homogeneous space. So in this case, like in genus 0, we actually get, get actually a smooth moduli space, smooth and proper. So they are like complex, compact orbifold of this expected dimension. Okay, so yeah, sorry, that's what I said. So if it's convex and for any number of mark point n and any degree, the obstruction shift is 0 on m bar 0 and x beta. It's a proper Deligne-Mumford, smooth Deligne-Mumford of this dimension. And in this case, this T1, I mean the T0, T2, the obstruction space. Oh, sorry, this should be T upper 2. I'll correct it. So then T upper 1, so the tangent spaces form a tangent sheaf in general, but in this case, it will be a vector bundle whose rank is equal to this virtual dimension, which is actually the actual dimension in this case. And the virtual fundamental class in this case is just the fundamental class. So that's the first example. So the second example is, so we consider constant stable maps, degree 0 stable maps. So this is, yeah, constant. So degree 0 stable map to X, it's just the same as the M bar GN cross X. Yeah, as a proper smooth Deligne. So this is isomorphic as a smooth Deligne-Mumford stack, and the right-hand side is smooth, right? X is smooth and bar GN is smooth. And in particular, we see that when the degree is 0, so this is non-empty if and only if M bar GN is non-empty. And this isomorphism is like to send the stable map to. Yeah, I think the first projection to the first factor is just forgetting the map and project. Yeah, and then this is just tells you like the image of that constant map. So now we can actually look at this example and look at the short exact sequences using this identification, right? So if we have, so suppose that we have a point in this, genus 0. We have a point which is a genus, it's a genus G M pointed constant stable map, which is given by a pair, like a stable, actually a genus G M point stable curve together with a point P in the target capital X. So then this is just the automorphism. This is the automorphism of the domain as a marked curve. But since the curve is already stable, so this is 0. And this part is a deformation of the curve. But this is the tangent space of M bar GN at this point. So now here, this is the deformation of, but you see H0C, the pullback of Tx. But in this case, this U is a constant map to the point P. So this is identified with the tangent space of X at P. And here, this is the constant map. So now here's more interesting because it's a constant map. So this is isomorphic to H1 of C. This is the structure shift, the trivial line bundle, times the tangent space, tensor the tangent space to X at P. And this is the fiber of the dual of the Hodge bundle. So the Hodge bundle of the modulus of M bar GN is a rank G bundle whose fibers are sections of the dualizing sheaf. When the domain is smooth, this is just a space of holomorphic one form. So it's a genus G vector space at any point. And it can be extended to M bar Gn, and that's the Hodge bundle. And this is the dual of the Hodge bundle. Okay, so you see that. So in this case, the moduli is smooth. But the thing is so this has some actual dimension, which is 3G minus 3 plus M plus the dimension of X. But it's not equal to the virtual dimension if we view it as like moduli space of degree 0 stable maps. And so so this is not 0. So in this case, the tangent sheaf and obstruction sheaf T1 and T2, they are actually vector bundles. So the virtual, so on the left-hand side, the virtual vector bundle is like tangent. Now it's smooth, so it actually has a tangent bundle. So T1 is its tangent bundle, but it also has an obstruction bundle. So the left-hand side, the virtual tangent bundle is equal to its tangent bundle minus the minus obstruction bundle, which is you pull back the dual of the Hodge bundle tensor with the pullback of the tangent bundle. And you see this is so the difference of this, so this has dimension G times, capital N is the dimension of the target. So now we have this equality of virtual class in this case. So this is a case where your moduli space is actually smooth, but the fundamental class is not equal to the fundamental class. So the difference is you take this fundamental class, which is, it's actually in Chao, but today let's think about homology. So it's the homology of this degree. So it's 2 times the complex dimension of this smooth orbifold. So since it's orbifold, so this fundamental class is like with rational coefficient. And then this vector bundle of rank Gn, so we take the top Euler class. So it's a cohomology class of degree 2 Gn, and we take the cap, and this will give us this. So this is in this case, the virtual fundamental class is the actual fundamental class cap the Euler class of the, this obstruction bundle. Okay, so that's, so next I want to talk about, Gromov-Witten invariance of Calabi-Yau threefolds. So at least from the point of view of Gromov-Witten invariance, so why are Calabi-Yau threefolds particularly nice? Of course, there are also motivation from string theory. So from the point of view of Gromov-Witten theory, let's look at this formula of virtual dimension. So if X is a Calabi-Yau threefold, so that means it's a projective threefold, or more generally, a Kähler threefold. So the complex dimension is 3. So this term goes away, and the Calabi-Yau condition means that the top exterior product of the tangent bundle is a trivial line bundle. The canonical line bundle is trivial. So in particular, the first chain class of the tangent bundle is 0. So then you see that this virtual dimension is just equal to the dimension of the mark point, and it's independent of the genus and the degree. And if we consider the moduli space with 0 mark point, then for any genus and any degree, we have a virtual fundamental class, which is a zeros homology class. in the moduli space. So for each genus and each degree, we define a Gromov-Witten invariant of this Calabi-Yau threefold by pairing this zeros homology class with the zeros cohomology class 1. And it's a rational number in general. So this should be viewed as the virtual number of points in this moduli space. Because suppose that this moduli space is like actually, so this has virtual dimension 0. Suppose this moduli space is actually smooth. Let's say a smooth complex manifold of dimension 0, then it just consists of finitely many points. And then the number of points should be given by this. So this should be viewed as generalization, like virtual number of points in this moduli space. Because in the general set, so in general, this moduli space can have, yeah, like positive dimension, and like it can have like different irreducible component have with different dimensions, and it's in general pretty singular. But this is the replacement of number of points. And then also it's rational number because this is a singular orbifold in general. So if you have a map which has automorphism group of order 2, you should count it as half a map instead of a map. That's how we get rational numbers. So when genus is greater or equal to 2, so the A model genus G free energy of this Calabi-Yau threefold is given by this generating function of genus G Gromov-Witten invariant sum over all degrees. So here Q beta is some like formal variable, like keeping track of like the different degrees. So at least like for A model topological, so this is like the mathematical definition of this A model genus G free energy. So when genus is like 0 and 1, because like because 0 mark points are unstable, so we need to add some other, it's slightly different. But this is the definition when genus is greater or equal to 2. So so here's a remark. So up to now for the general theory, so we assume the target is a projective manifold because under such assumption we can assume one can prove that the moduli space is actually proper or compact. So but indeed, if you consider like a target which is just quasi-projective, and then so you don't know if this is compact or proper, but it is still the Riemann stack. It still has a perfect obstruction theory of this virtual dimension, right? Because when we discuss this perfect obstruction theory and like this doesn't use the fact that this is proper. So we still have this structure of the Riemann stack, perfect obstruction theory. But now there are sometimes, because we will actually, you see this mini course later in part 2 and part 3, we will focus on toric Calabi-Yau threefolds, and they are never compact. But sometimes even if your Calabi-Yau threefold is non-compact, in some cases, so this moduli space happens to be compact. And then we can, then there is the fundamental class, and we can still define the G degree beta Gromov-Witten invariance for this particular G beta such that this moduli space is compact. So let me give you a couple of examples. So the first example is like so-called the resolved conical. So we consider the total space of O minus 1 plus O minus 1 over P1. And then P1 be the, so there's a projection to the base P1, and there's a map like zero section from the base to the total space X. So this, this projection is like homotopy equivalence. So the second homology of the, and this X is a non-compact Calabi-Yau threefold. And the second homology of X is equal to the second homology of the base, because this map is like, homotopy equivalence. So it's generated by the class of a line. This L is the fundamental class. So the inclusion of the zero section induces the inclusion of the moduli space, right? Because if you have any stable map to P1, you can compose it with this inclusion, you get a stable map to X. So we have this inclusion. But actually, this inclusion is an isomorphism if the degree is not zero. So if you have any non-constant map to this total space, it mass factors through this. And of course, because like, if degree is less than zero, then this is empty, because because the map is like holomorphic, so you cannot have negative degree. So you see, for the for this resolved conical, it's a non-compact Calabi-Yau threefold, but we can still apply the definition when degree is non-zero and define this Gromov-Witten invariance for this non-compact Calabi-Yau threefold. And the second example is similar. So we now consider the total space of the canonical line bundle over P2, which is O minus 3. And again, so let I0 be the inclusion of the zero section. And again, the projection from X to P2 is a homotopy equivalence. So the second homology of X is the same as the second homology of the base, which is generated by the class of a projective line in P2. And again, so the inclusion of the zero section gives you an inclusion of the moduli spaces. Oh yes, maybe it's, because this is the isomorphism. Yeah, sorry, I go back to the previous example. When D is not equal to zero, this inclusion is an isomorphism. And then, but the stable map to P1 is compact because P1 is compact. Okay, so now similarly, we again can show that like when degree is, this is the typo, when degree is less than zero, this moduli space is empty. So when degree is greater than zero, this inclusion is an isomorphism. So we know the moduli space of stable maps to X is actually proper when the degree is positive, and we can define Gromov-Witten invariance. So of course, when the degree is zero, we have seen that the moduli space is M bar G0 cross X. So then in that case, this inclusion is not an isomorphism. And in this case, the moduli space of degree 0 stable map to X is not proper because X is not proper. Okay, so this is another similar example where Gromov-Witten invariance of the X is defined for most of the degrees, though the target is a non-compact Calabi-Yau threefold. Yeah, so maybe I'll say that so example 1 and 2 are toric Calabi-Yau threefolds, yeah, which I think I'll define more precisely next time. So a Calabi-Yau threefold X is toric if it contains the C algebraic torus C star 3 as an open dense subset, and the action of C star 3 on itself extend to an algebraic action on X. And yeah, you can see that the O-1 plus O- over P1 and O-3 over P2, they are examples of toric Calabi-Yau threefolds. And as I said, mentioned earlier, a toric Calabi-Yau threefold is never compact, but we have just seen that actually we can still define their Gromov-Witten invariance in many cases. So what the topological, so we have this X, so each genus and each degree, we have this invariant. So in the second part of this mini course, the topological vertex actually provides a closed formula for this generating function where we fix the degree and sum over the genus of the map. So on the other hand, the remodeling conjecture is somehow a different algorithm. So it provides an algorithm to compute FG where you fix the genus and sum over the degrees. Okay, so now next, so these are like Calabi-Yau threefolds. So next, I want to so talk about more general Gromov-Witten invariants for a general target projective manifold of any dimension. Recall that we have this evaluation map EVI at the I-smart point. So we can pull back the cohomology of the target X to the moduli space. So this gives us some cohomology classes on the moduli space. So there are other cohomology classes. So that omega might be the relative dualizing sheaf. So it's just the like vertical dualizing sheaf. When it's so when the fiber is a smooth curve, this is just the like the vertical cotangent bundle. So let's consider, so Li is if you so this Li is a line bundle over the moduli space whose fiber whose fiber over this moduli point is the cotangent line at the I-smart point. So the I-smart point is smooth. So we have for each mark point, for each I, we have this Li, and the psi classes are just the first chain class. So it's a second cohomology class with rational coefficient, because in general, these line bundles are orbifold line bundles. So in general, we get some class with rational coefficient. Yeah, we want to consider the rational cohomology, which we identify with the like coarse moduli, the rational cohomology of the coarse moduli space. Sorry, oh, you usually, so there's a comment, oh, your comment,
Yeah.
you usually have to use virtual moduli space since the original moduli space is singular. Oh, sorry, I missed the comments. Sorry, that was half an hour ago. So maybe can you say it?
The question is why are these local Calabi-Yau manifold interested in string theory? What will be different from considering local and global Calabi-Yau manifolds? This is the first question.
Oh, yeah, for the string theory, maybe I think maybe Daniel is better at answering such question. Would you please? Yeah, so global Calabi-Yau manifolds, yeah, I guess the work which motivated the development of Gromov-Witten theory is like so it's the prediction about rational curves in a quintic threefold, which is a compact Calabi-Yau threefold. So it is much harder to compute the higher genus Gromov-Witten invariance or compact Calabi-Yau threefolds. So yeah, since you asked, maybe next time I can summarize some progress even for this quintic threefold whose like genus zero invariants were completely known in the 90s. But now, the higher genus invariants are still, I guess I heard that it has been like Clem and collaborators, I think now they can do up to 64 maybe. Yeah, so maybe I'll say more next time. So, but then this toric Calabi-Yau threefolds are easier so that we can actually solve it completely and we know the structures. So that will be the difference from the point of view of like a model topological string, the compact Calabi-Yau threefolds. The higher genus invariants of compact Calabi-Yau threefolds are much more difficult than this toric Calabi-Yau threefolds. And moreover, for this toric Calabi-Yau threefolds, we can even define and compute open Gromov-Witten invariants. So for compact Calabi-Yau threefold in general, like it's not even clear how to define higher genus open Gromov-Witten invariants. Oh, I see.
And the other,
Uh,
and the other question is that suppose the moduli space of a stable maps is compact, but the target space X is a non-compact Calabi-Yau threefold. Does that imply that S is toric?
No. For example, you can, let's see. So you can, you can consider instead of the O minus 3 over P2 example, you can replace the base by a Del Paso surface, which is not toric. So you can still get so then and you have similar, you can, I think the stable map is still compact in some cases, and the target is non-compact, but it's not necessarily toric. So suppose that I hope this answers that question. Suppose the moduli space of stable map is compact, but the target space X is non-compact, Calabi-Yau threefold. So this does not imply that X is toric. Right, so so the next example is what are some efficient computational techniques to calculate this invariance? In the case of flat varieties, for example, can you compute this invariance using combinatorial structure of the spaces? Yeah, so one of the tools to compute this invariance is via torus localization. So I guess when you, sorry, someone already answered the question. The answer is Bunsi-Kim computed some Gromov-Witten invariance of some flat varieties using localization. Yeah, great. So yeah, thank you. So this is okay. So yeah, I think all the answers have been questions have been answered by me or by the audience. So okay, so I think right now maybe I can continue. Yes. Right, in general, like when the flat variety, or I mean the thing is this toric or flat variety, so there's some torus action on your target X, which will induce this torus action on the moduli space. And you can use this torus action to compute Gromov-Witten invariance. Actually, that's essentially our main tool to solve this topological vertex and the remodeling conjecture. So we will say more about that later. Right. So yeah, so maybe let me continue. So so we have defined the psi classes, which is like first chain class of this line bundles coming from the cotangent line at the mark points. And also recall we have this Hodge. So sorry, we can define, I guess we have seen the Hodge bundle on M bar Gn, but we can also define the Hodge bundle for M bar Gn X beta. So this is the fiber over the Hodge bundle H0 is the space of sections of the dualizing sheaf. When C is smooth, this is just a space of when C is smooth, we can view it as a compact Riemann surface, and this is just the space of holomorphic one forms. So this is a vector bundle over rank G. So we define lambda classes to be the chain classes of the Hodge bundle. This can be defined over M bar G and X beta. So finally, so we can consider, so recall that from M bar G and X beta, there's a forgetful map. By forgetting the map U and just remember the domain. So now we can further, there's a map from the like pre-stable Gina G M pointed pre-stable maps to the moduli M bar Gn to stable maps. So we just contract the unstable component to make it stable. So there's such a map. So let's call this map P, right? We have this map P from M bar Gn X beta to M bar Gn. Let's call this P. And now on M bar Gn, we have these psi classes on M bar Gn. And in general, so psi, so if you just pull back the psi, so there's a psi class on the moduli of pre-stable curves. And if you, because when we forget the map, we don't do anything to the pre-stable curve. We don't do anything with the domain. So if you pull back the psi class on the moduli, say, so pre-stable curves, this is equal. And this is like called gravitational descendants. And so maybe Daniel can tell you why they are called gravitational descendants. And so and then if you pull it back via P, so then because there's some contraction involved, so the pullback of psi on M bar Gn, they are not so this psi is the psi on M bar Gn, the pullback is not equal to psi class on M bar Gn X beta, and we call them psi I bar. Okay, so maybe I don't know if Daniel wants to say something about why these are called gravitational descendants.
Okay.
Thank you. So so these are the so we are going to define these correlators, which I think Daniel just mentioned. So we take So the thing is, we have this virtual fundamental class. It's a homology class. We can pair it with cohomology class. Yeah, so maybe, so let's, yeah, so we probably don't want to worry about the signs, like involving switching this. So let's just consider even cohomology classes so that we don't need to worry about the sign of involving like the cup product. So yeah, so let's see. So you see this virtual fundamental class will, like, if we are given some cohomology class on the moduli space, pairing with this virtual fundamental class will decrease the, yeah, so sorry. So this will yeah, but basically, yeah, this is just saying that we get 0 unless the degree matches with this, and in this case we get a rational number. So now let's see. So we take some cohomology class. Let's, for simplicity, assume they are even on X. And we also take A1 to AN, which are non-negative integers, and then we define this a correlator. They are descendant Gromov-Witten invariants of X. So it's defined the following way. So for each mark point, we take the psi I to the AI's power and take the pullback of gamma I under the evaluation map EVI. And then this is some cohomology class, and we pair with the fundamental class to get a rational number. So we know that the degree of this cohomology class is like twice of the sum of AI plus KI. So this is 0 unless this is equal to the virtual dimension of the moduli space. So these are like correlators defined by, like, these are gravitational descendants. But we can also replace, in this definition, we replace the descendant by ancestors, and then they are called psi bar, and they are called ancestor Gromov-Witten invariants. Yeah, so it's, let's see, so we have, okay, maybe let's see, I don't know if yes, so right, so we have descendant Gromov-Witten invariants and ancestor Gromov-Witten invariants, and they satisfy some axioms. So in the next section, so the axioms for ancestor Gromov-Witten invariants can be formulated in terms of cohomological field theory, CoFT. And there are also the axioms of descendant Gromov-Witten invariants. They are known as string equation, divisor equation, and dilaton equations. So, but maybe because since I only have about 5 minutes, maybe it's better to start this next time.
Okay, great. Then let's thanks Melissa for this really nice first talk.
Oh,
and
thank you.
then let's see if there is any question.
So yeah, so there's some question. What are these descendant and ancestor invariants counting? I'm not sure I understand the idea here. Okay, so you can think it in the following way. So yeah, so maybe, oh, I forget. So let's consider the case. Oh, yeah, actually I forgot to say one more thing, is when So the primary invariants are when all the AIs are 0, and then when all the AIs are 0, so first let me say when all the AIs are 0, then this is called the primary invariance, and then this correlator when all the AIs are 0 can be think of some, like when everything is very nice and transversal, like this flag variety is genus 0. But in general, these are like you want to have some virtual count of genus G degree beta curve, parameterized curves passing through cycles which are Poincare dual of this cohomology classes. So that's the when everything is transversal, that's the enumerative meaning. But because things are highly non-transversal, so so this is the virtual count. So now, what if we have gravitational descendant? So this psi class, you can think that it put further constraint, because this, so maybe it's easier to say it in terms of the ancestor. So for the ancestor, you can think that this psi I bar, so it puts some constraint on the complex structure of the domain curve. So it's like you want the curve to pass through, you fix genus degree and you want the curve to pass some like cycles on the target, but you also have some constraint about the complex structure of the domain. That's a rough idea, but then this might be like more, so next time we will talk about co-FT. So I'll just maybe it will be even clearer when we think it in terms of co-FT. So I hope this answers the question. And also, can you recommend some reference for physics and mathematicians? So I have some recommendation, maybe, Danny will have. I saw there's a list in Daniel's lecture. So for physics and so I will recommend there's a big book called Mirror Symmetry. So it is the outcome of some spring school of clay math in 2000. I participated as a graduate student. And basically what happens, they have physicists and mathematicians, young physicists and mathematicians, where they give crash course on mathematics to young physicists and crash course of physics to young mathematicians. So this is one of the reference I can recommend.